The universe is a vast and ever-changing expanse. It's filled with celestial wonders that continue to amaze us. Among these spectacular events are novae, sudden bursts of energy that illuminate the cosmos. Imagine a star, seemingly insignificant, suddenly flaring to life. It becomes thousands of times brighter, shining like a cosmic beacon. This, my friends, is the captivating phenomenon of a nova. A nova is not simply a star being born, it's a dramatic outburst, a cataclysmic event that occurs on the surface of a white dwarf star. However, novae are not as destructive as their more powerful cousins, supernovae. While a supernova signals the death of a star, a nova is more of a cosmic rebirth. Novae are fascinating events that give us a glimpse into the extreme conditions that exist in our universe. They remind us that even in the depths of space, change is the only constant. In the next section, we will delve into the heart of a nova, exploring the binary star systems that serve as the engine for these explosive events. Get ready to explore the fascinating world of stellar interactions and cosmic cataclysms. To understand the origins of a nova, we must first journey into the heart of a binary star system. A binary star system, as the name suggests, consists of two stars that are gravitationally bound to each other. They orbit a common center of mass, engaged in a celestial dance that has profound consequences. In the case of novae, one of these stars is a white dwarf. A white dwarf is the remnant of a star like our Sun that has exhausted its nuclear fuel. It is incredibly dense, packing the mass of the Sun into a sphere roughly the size of Earth. The other star in this cosmic partnership is typically a main sequence star, similar to our own Sun, or a red giant, a star in the later stages of its life. The white dwarf, with its intense gravitational pull, acts like a cosmic vacuum cleaner. It draws in hydrogen-rich material from its companion star. This material forms a swirling disk of gas and dust around the white dwarf, known as an accretion disk. This accretion disk is the stage for the dramatic events that lead to a nova. The next section will delve into the details of this process, revealing how the white dwarf's insatiable appetite for matter sets the stage for a cosmic explosion. Imagine a celestial feast where the white dwarf star is the hungry guest, and its companion star is the unwilling host. The white dwarf, with its powerful gravity, pulls in a stream of hydrogen gas from its companion. This stream of gas spirals inwards, forming a swirling disk of material around the white dwarf. This process, known as accretion, is a slow and steady accumulation of matter. Think of it as a cosmic drizzle, slowly but surely adding to the white dwarf's outer layers. As more and more hydrogen gas is pulled in, the accretion disk becomes denser and hotter. The temperature at the base of this disk, where it meets the surface of the white dwarf, can reach millions of degrees. This intense heat and pressure are the key ingredients for the thermonuclear runaway reaction that powers a nova. The white dwarf, once a dormant stellar remnant, is about to experience a dramatic resurgence. The stage is set. The white dwarf, with its insatiable appetite, has been steadily accumulating hydrogen from its companion star. The accretion disk, a swirling maelstrom of hot gas, has been heating up under intense pressure. Now, the critical moment arrives. The temperature and pressure at the base of the accretion disk reach a tipping point. At this critical juncture, the hydrogen atoms, normally resistant to fusion, are forced together with incredible force. This triggers a runaway thermonuclear reaction. It's like igniting a colossal hydrogen bomb on the surface of the white dwarf. This sudden release of energy produces a brilliant flash of light that we observe as a nova. The white dwarf, once a dim ember in the vastness of space, erupts in a blaze of glory. It can shine thousands of times brighter than its normal luminosity, becoming a beacon visible across vast cosmic distances. The universe is a diverse place, and novae are no exception. Just like there are different types of stars, there are also different types of novae, each with its own unique characteristics. The most common type is the classical nova. These are one-time events where the white dwarf undergoes a single, massive outburst. Then we have the recurrent novae, which, as their name suggests, erupt multiple times. These novae occur in binary systems. This is more balanced, allowing for multiple cycles of buildup and explosion. Another intriguing type is the dwarf nova. Don't let the name fool you. These events are still incredibly energetic. They are less luminous than classical novae and occur more frequently. dwarf novae are thought to be caused by instabilities in the accretion disk itself, rather than a full-blown thermonuclear runaway on the white dwarf's surface. These different novae provide astronomers with valuable insights into the dynamics of binary star systems and the processes that drive these explosive events. Each nova is a unique story, a cosmic grand stage. Section 6. Novae versus supernovae, a tale of two explosions. Novae and supernovae are often mentioned in the same breath, and for good reason. Both involve the spectacular deaths of stars, but they are fundamentally different events. Think of novae as powerful fireworks, while supernovae are more like cosmic bombs. A nova is a surface explosion. It occurs on the surface of a white dwarf in a binary system, fueled by the accumulated hydrogen from its companion star. The white dwarf itself survives the explosion, like a phoenix rising from the ashes. It can continue to accrete matter, setting the stage for future nova events. A supernova, on the other hand, is the complete destruction of a star. It is a much more energetic event, releasing 1,000 times more energy than a nova. Supernovae occur when a massive star runs out of fuel and collapses under its own gravity, or when a white dwarf in a binary system accretes too much mass, triggering a runaway nuclear explosion that obliterates the star. While novae might seem less impressive in comparison, they are still incredibly powerful events. They provide valuable insights into stellar evolution, the dynamics of binary systems, and the extreme conditions that exist in our universe. Section 7. The afterglow of a nova. Remnants and Recurrence. After the brilliant flash of a nova fades, what remains? The answer lies in the remnants of the explosion, and the potential for future outbursts. The ejected material, rich in heavy elements, expands outwards, creating a beautiful expanding shell of gas and dust. This shell, known as a nova remnant, can be observed for centuries after the initial explosion. The fate of the binary system itself depends on the type of nova and the amount of mass lost during the explosion. In some cases, the binary system may survive, with the white dwarf continuing to accrete material from its companion star. This sets the stage for recurrent novae, where the cycle of accretion and explosion can repeat multiple times. The study of nova remnants and the recurrence of novae provides astronomers with valuable clues about the long-term evolution of binary systems and the processes that drive these explosive events. Section 8. Recent nova sightings, catching the show. Novae are not just theoretical phenomena, they are real events that occur regularly in our galaxy and beyond. In recent years, astronomers have observed numerous novae, each providing a unique glimpse into these explosive events. One notable example is V1674 Hercules, a fast nova that erupted in June 2021. This nova was unusual for its rapid brightening and decline, reaching peak brightness in less than a day. Another recent event is RS Ophiuchi, a recurrent nova that erupted in August 2021. This nova is particularly interesting because it occurs in a binary system where one of the stars is a red giant. These recent nova sightings highlight the ongoing activity in our universe and the importance of continued observation and study. By studying these events, we gain a deeper understanding of the processes that shape the cosmos. Section 9. Conclusion. The enduring mystery of novae. Novae are a captivating testament to the dynamic and ever-changing nature of our universe. These cosmic explosions, though less powerful than supernovae, are no less fascinating. They provide a glimpse into the extreme conditions that exist in binary star systems and the processes that drive stellar evolution. While we have learned much about novae, many mysteries remain. The exact mechanisms that trigger these explosions, the long-term fate of the binary systems involved, and the role of novae in enriching the interstellar medium with heavy elements are all areas of ongoing research. As we continue to explore the cosmos, we can be sure that novae will continue to surprise and amaze us. These celestial fireworks, with their brilliant flashes and enduring afterglows, serve as a reminder of the vastness of the universe and the endless wonders it holds.